audio check. Okay, very good afternoon to all of you. Today we will start the design step to design the destination column. Before this, just I would like to recall all the previous topics whatever we discussed. As in the previous topic, we have discussed the downcomer backup, and also we are able to know why the diameter of vacuum column is more than diameter of atmospheric column. So these all things we have discussed, and also we have seen the Francis equation या Francis curve. तो threading velocity निकालने के लिए हम क्या करेंगे? To find the threading velocity, we should know the kV, and to find the kV, we should know the one parameter called as L upon V under root rho V upon rho L, and as a parameter of plate spacing. So these all things we have discussed. So now in the same sequence, the next part is, as I told you one thing, operating range. As far as operating range is concerned, I have told you that we are not supposed to increase the velocity of vapor very high, because if the velocity of vapor will be very high, then flooding will take place, and if the velocity of vapor is very low, then weeping may takes place. That's why the operating range of the vapor and liquid, the same thing is also going to happen with the liquid, because flooding can take place not only with the increase in the vapor flow rate, but also due to increase in the liquid flow rate. The main purpose of flooding is what? Pressure drop, increase in pressure drop. So main thing is that the liquid and vapor flow rate should not be very high and should not be very low. It means the range in which we are going to operate our column is very limited, and that is the reason I am going to discuss here. One is called as operating range, means in which range the liquid and vapor flow rate can be operate in a column. Now satisfactory operation will be only achieved over limited range. Satisfactory operation will only be achieved over a limited range of vapor and liquid flow rates. Means there is only limited range of vapor and liquid where we can operate our column satisfactorily. A typical performance diagram for a sieve plate is shown in the figure. That figure I have taken from the RC volume 6. This is the vapor flow rate, and this axis is the liquid flow rate. And we are going to see that, Priyan sir, इसको बता दीजिए कि लिंक चेक कर लीजिए, ओपन हो गया है कॉल। Now vapor flow rate and liquid flow rate. If a liquid flow rate is too low, if liquid flow rate is too low, you can see here, in that condition the weeping will take place here. It is weeping. If the liquid flow rate is too low, then weeping will take place. And the coning I have told you, when the vapor flow rate is very high, then this will push, that vapor will push the liquid away, and the poor contact between vapor and liquid will take place. So that is called as coning. So coning will take place when the vapor fluid is very high and liquid fluid is very low. Is it right? At the same time, in this case, downcomer backup limitation will downcomer backup problem is also there. Downcomer backup problem means the liquid is start accumulate in downcomer, and the main reason of downcomer is when the vapor and liquid fluid both is high, then pressure drop will take place. Okay. Flooding will take place when vapor fluid is too high and liquid fluid is moderate to low, then flooding will take place. Excessive entrainment will also take place when the vapor fluid is high and liquid fluid is low. So that is the case here, and because when the entrainment will take place, then worst case of entrainment is called flooding actually. So we are not able to operate the vapor and liquid beyond that region. Only we are able to operate satisfactorily in that region. The area of satisfactory operation is only very limited. This is the region where we are going to operate our column satisfactorily with the vapor and liquid fluids. Now, this all the data, all the remaining slides I have taken from the RC volume 6 for the design. It is design book, design for mass transfer equipments and heat exchange equipment as well. Plate design procedure or trial and error, because design is totally based on trial and error, because we have to assume some data, and on the behalf of that assumed data we will calculate the remaining data, and if it is going to obtain, if the result is going to obtain under satisfactory reason, then it is correct whatever we assume. Otherwise we have to further reverse back to that steps. So a trial and error approach is required in the plate design. Starting with rough plate layout means what should be the diameter of the plate, what should be the holes diameter in the plate. जो भी plate होगा, sieve plate लेते हैं, bubble cap लेते हैं, whatever is there. So what should be diameter? How many number of holes should be there? What should be the hole area? What should be perforation area? What should be the column area? And what should be the downcomer area? This all is called as plate layout. Checking key performance factor. Key performance factor means the factor which are going to affect the performance of a column, that is weeping, flooding, downcomer backups, all the things. Until a satisfactory design is achieved, means that process we have assumed something, we have assumed some variables, and on the behalf of that assumed variable we will calculate the other parameters until we are not reaching at the satisfactory level, and once satisfactory results is obtained, then whatever we assume data, that data is used for the design. A typical design procedure is set out below and discussed in the following section. Means every step I will discuss in later on, but at least we should know what steps we should follow here. Now, to design the plate column, to design the plate, what procedure we should follow, that I am going to discuss here. The first I am going to discuss is the first step is calculate the maximum and minimum vapor and liquid fluids for the turn down ratio required. Turn down ratio is defined as, I told you many times, turn down ratio is very important parameter in design point of view, and that is anything which is maximum to its minimum value. Ratio of maximum to minimum is called as turn down ratio. And in this case, the maximum vapor and minimum vapor and liquid fluid is very important, and that we can obtain by the material balance of calculation. Material balance, energy balance, whatever balance we will apply, I will discuss one by example. But first of all, we should know what is the value of V bar and L bar, vapor and liquid fluid in the stripping section, and V and L, vapor and liquid fluid in the rectifying section. So first of all, we should know what is the maximum and minimum vapor and liquid fluids. Okay, So how we'll find out these all things I will discuss by numerical problem, but just try to recall the step first. Second, collect or estimate the system physical properties. System physical properties means we should calculate the density of vapor and density of liquid, surface tension sometime also, at the top and bottom of the column respectively. Bottom means stepping section and top means rectifying section, because temperature and pressure at the top of the column is different, and temperature and pressure at the top and bottom at the bottom of the column will be different, and that's why the property of the fluid will also be changed, called as physical properties like density, viscosity, all the things. The first step is that we have to calculate the vapor and liquid fluids in both section. Second, we should calculate or assume or estimate from the data handbook at a given temperature and pressure what should be the physical properties, density and viscosity of the liquid, all the things. And third very important step is that, because here this is called as assumption, we have to assume, select a trial plate spacing. Trial plate spacing means we have to assume a spacing. Spacing means the distance between the two adjacent plate is called as plate spacing. So that plate spacing is very important. So for this we have to assume any trial value for the plate spacing. Now, and estimate the column diameter based on flooding consideration. I have told you in the last lecture how will you calculate the diameter of the column, either rectifying or stepping, on the behalf of flooding velocity. By knowing the flooding velocity, just I am going to discuss here, I am going to recall that maximum velocity of the vapor is here kV into under root rho L minus rho V upon rho V. Clear? And the value of kV we can calculate. Listen, step is very very important. kV, it is L upon V under root rho V upon rho L, and this is the parameter here. These types of curve we have seen. Now, and this parameter is plate spacing. So already in the third step we have assumed the plate spacing, and once we have assumed the plate spacing and we have already calculated the physical properties rho L and rho V, I have told you in the second step. Very important thing, everything is very proper way, everything is here in the very proper way, and this is the step what we should follow during the design of plate. So in this case what happened, first of all, first step, once again I am going to recall, the first step is we have to calculate the maximum and minimum vapor fluid by the material balance. I will discuss in the example. Second is collect or estimate the system physical properties from data handbook, from a steam table, whatever is there, because temperature and pressure at the bottom and top of the column is different, and that's why the properties of the fluid called as density of the vapor and liquid will be differ from top to bottom. And once third step is trial, take a trial value of plate spacing, assume the plate spacing, and once the plate spacing is assumed, on the behalf of that, once the plate spacing is assumed, on the behalf of that, from this curve we should calculate the value of kV, and just put the kV, you will able to find out the maximum vapor velocity, or maximum vapor velocity, or you can say incipient of entrainment velocity. And once we are able to calculate, once we will calculate the maximum velocity vapor, then the operating velocity should be lower than the flooding velocity called as maximum velocity here. So, and on the behalf of that we should calculate the diameter, because I told you V bar is equal to rho into column area, sorry, net area actually, into velocity, operating velocity. And this operating velocity is somewhat, let's say 20 to 40% of flooding velocity. And flooding velocity already we have calculated by knowing the plate spacing and by knowing the physical properties of the fluid. Then and V bar already I have calculated in the first step, vapor fluids, and then on the behalf of this density vapor is already known to you, and then we can calculate the AN is called net area, And once the net area is there, we can calculate the column diameter by assuming that down comma area is somewhat 10% or 20% of the whole column area. So this is the step how we will calculate the column diameter. Now, to estimate the column diameter based on the flooding consideration, that is your flooding consideration I told you. Now decide the liquid flow arrangement. Now then we will discuss about the liquid flow arrangements, because over the plate, over the tray deck, the different types of arrangements of the liquid is there. Different type of arrangement of the liquid is there. It may be cross flow, double pass flow, single pass flow. So different types of arrangements are there, and these arrangements I will discuss. That will depend upon some parameter. It depends upon the liquid flow rates, and one more parameter is there that you are able to know in the subsequent slides. So what types of arrangement is there over the plate? It is cross flow or double cross flow or single flow. So that we should decide on the behalf of some parameters. Now after that, make a trial plate layout. Make a trial plate layout. Trial plate layout, again it is trial plate layout, means we have to assume that downcomer area kitna hoga. Downcomer area is 10 to 20%. Now active area, I told you in the last lecture, active area is the also called as bubbling area. It is column area minus 2 times downcomer area. I told you already. Whole area over the sieve plate, whatever holes are there, perforations are there, what is the area of the one hole, hole size, wear height, all the things we should be, that is, these are all the parameters we should be assumed on the behalf of our previous calculations, or on the behalf of experience. So any value we can assume, because it is totally trial and error method. Now then thereafter we will should check the whipping rate. Means whipping rate means whatever the operating velocity we have calculated here, this operating velocity should be obviously much more than whipping rate. Otherwise whipping phenomena will take place, and that will reduce the efficiency of the column. So how will we check the whipping rate? There is a empirical correlation is there, and on the behalf of that empirical correlation we are able to find out is our operating velocity of vapor is more than whipping velocity or not. And if your operating velocity is just above or equal to or lower than the whipping velocity, minimum velocity called as whipping velocity, then obviously we should go for return to the step number 6. Because reason is there, because I will discuss and you will also show in the next slide that the whipping velocity UW, whipping velocity means minimum velocity vapor, where the whipping will start, that we can only find out on the behalf of parameters whatever we have assumed in the step number 6, is on the behalf of downcomer area, active area, whole area, all the things. And that's why if operating velocity of the vapor is equal to or lower than, or if difference in the operating and whipping velocity is not so much, in that condition we have to further change the trial value of the step number 6. We have to change the downcomer area, we have to change the plate layouts, all the things. Clear? Now, and thereafter, suppose if it is satisfactory, then no need to worry, then we will proceed the next step. Check the plate pressure drop. And I have told you already how many types of pressure drop is there over the tray. The tray pressure drop is summation of dry frictional dry plate pressure drop, and the second is called as hydrostatic head of the liquid over the tray. So in दोनों summation होगा, that is called as tray plate pressure drop. And जो liquid होगा कितना होगा, HD plus HW plus HOW into beta plus ये तो हो गया, plus frictional loss जो होगा that is called as HD, and HD I have told you it is proportional to velocity of vapor का square. Already I have given the correlation in the previous lecture. Okay. Now, if too high, if the pressure drop across the plate is too high, then again return to step number 6, because by changing the plate layout we are able to calculate the pressure drop in satisfactory region. Means until we should vary the step number 6 until unless we will not be in the satisfactory region for the pressure drop over the stage. Now and thereafter check the downcomer backup. Now downcomer backup means height of the liquid in the downcomer, and the height of the liquid in downcomer is equal to, I told you formula for this. This is HFL plus 2 times beta into SW plus HOW and plus HD. Okay, that I have told you in the last lecture. And if downcomer backup is too high, return to step number 6 or step number 3, because 3 and 6 step number is the trial value. Here we have assumed some data, because I told you if downcomer backup is very high and if it is equal to plate spacing, then obviously what happens, the flooding will take place, and either we can change the plate layout or we can increase the plate spacing. By increasing the plate spacing, we are able to reduce the phenomena of flooding. Now thereafter decide the plate layout details. Whatever we have assumed on the behalf of that plate layout we have assumed first, then if everything is in the limit, then on the behalf of that downcomer area, active area and whole size, whatever plate layout we have assumed, if on the behalf of this values of the plate layouts, if all things means weeping is satisfactory, pressure drop is satisfactory and downcomer backup is satisfactory, then we will further design the plate layout on the behalf of whatever value we have assumed. Means in this case we will calculate the calming zone unperforated area and check the whole pitch. If satisfactory, then we will calculate the whole pitch, and if it is satisfactory, then clear. Otherwise we should go for the step number 6 again. Now recalculate the percentage flooding based on the chosen column diameter. Whatever column diameter we have chosen, whatever column data we have found out, on the behalf of that we should again calculate the percentage flooding. Okay, now and thereafter we'll check the entrainment is high or low, and after that all the things we've checked, and then we'll optimize the design. Okay, and repeat the step number 3 to 12 here to find the smallest diameter and plate spacing acceptable at the lowest cost. It is part of optimization how the cost will minimize, and finalize draw of the plate specification and discuss the layout. So this is called as plate design procedure, and these all steps will be more clear in the subsequent slides. Listen, before this I would like to discuss plate areas. I have already discussed, but still I am going to further recall. AC is called as total column cross sectional area, AD is called as cross sectional area of downcomer, also called as downcomer area, AN is called as the net area available for vapor liquid disengagement, and normally it is equal to AC minus AD for a single pass plate. Single pass मैंने कहा था types of flow pattern, and as far as types of flow pattern is concerned, there is a cross flow, single pass, double pass. This you are able to know in the next slides. Active area or also called bubbling area, that is AC minus 2AD, means जो कॉलम होता है उसमें ये प्लेट है, तो this area we have subtracted out, only this area is called as bubbling area, also called as active area. AH is called as whole area or total area of all active holes. So whatever holes over the stage is there, सबका जो area होगा that is called as whole area AH, and perforated area including blanketed area, so it is area of perforations, and AAP is called as the clearance area under the downcomer apron. That you are able to know in the next lecture. The main thing is that areas are there, and they are notations. Now as I told you already, we have discussed about the flooding consideration in the last lecture, and we have discussed how we are able to find the value of kV on the view of kV and plate spacing, and L upon V we will able to calculate the value of flooding velocity. And the next is called liquid flow arrangement. The choice of the plate type. Plate can be of the different type, reverse, single pass, multiple pass, will depend upon the liquid flow rate and column diameter. Actually, what types of plate, because the plate will be also be of different type, the what types of plate we should choose, that will depend upon the liquid flow rate and column diameter. So before this, if you see in this slide, that the flow arrangements we have chosen only after finding out the column diameter. So before choosing the arrangement of the flow over the stage, we should first calculate the diameter. Reason is that because flow arrangements we can only be find out on by knowing the liquid flow rates as well as diameter of the column. It is diameter DE or DC. So column diameter is known to you. Liquid flow arrangement already L bar or L we have calculated out in the first step. On the behalf of that, we should know what types of flow: cross flow called as single pass, double pass, and reverse flow. So these different types of flow is there, and for this is the figure here. So an initial selection can be made using this figure, which has been adapted from a similar figure by Huang and Hodgson, or Huang and Hodgson. The main thing is that on the behalf of liquid flow rate and on the behalf of diameter of the column, we will be able to decide which types of flow will be better: single pass flow, cross flow called also, and double pass flow or reverse flow. Now then we will check for entrainment. The entrainment can be estimated from the correlation given by the figure, and this figure 11.29, which gives the fractional entrainment called as psi. Psi here is called as fractional entrainment as a function of liquid vapor factor, FLV. FLV is called as liquid vapor factor with the percentage approach to the flooding as parameter. Now here parameter is what? Parameter is actually, listen, in this case percentage flood is a parameter, I told you. In this case, first of all, fractional entrainment is called as psi here, and it is a FLV is a factor. So on the behalf of FLV, and FLV is obviously, I've told you, in this case FLV is just like kV actually, because previously kV I have told you flooding velocity is equal to kV into under root rho L minus rho V upon rho V, and this kV we have calculated from this chart as a function of L upon V under root rho V upon rho L, like that, plate displacing parameter. So this was the data kV they have used in the Maccabe Smith, and in the Coulson Richardson they are going to use the FLV. So meaning is same here, no need to worry about that. So FLV is given to you because FLV is what? Just like kV, and kV की जो value होगी वो हम निकाल चुके हैं on the behalf of this. And then by knowing the percentage of flood, listen here, as a function of liquid vapor factor with the percentage approach to the flooding as a parameter, the percentage flooding is defined as ratio of actual velocity based on actual area upon flooding velocity actually. So actual velocity upon flooding velocity called percentage of flooding. It is very simple. मान लो flooding velocity मान लिया 5 मीटर पर सेकंड है वेपर की, और actual velocity है 2.5 मीटर पर सेकंड है. Then obviously the percentage of flooding is about 50%. So by this way we are able to calculate the percentage flood. Percentage flood आपको मिल जाएगा because already we have calculated the flooding velocity. Already we are going to use the actual velocity. Actual velocity is somewhat 20 to 50% of the flooding velocity. So on the behalf of percentage flood as a parameter, let's say it will be 30%, 35%, 40%, 45%, 50%, 60, 70, any parameter. Let's say if we are going to operate our column as a 60% of the flooding velocity, 60% of flooding velocity, it means 0.6. And this FLV is just like kV, we have already used in the previous section. Then we can find out the percentage of fractional entrainment. Okay, and the effect of entrainment on the plate efficiency can be find out by the equation 11.78. Actually, by knowing the value of fractional entrainment, we are able to calculate the efficiency, and that's why this parameter is important. to find the entrainment. Are you getting? Now, and then the very important thing is called a weave point. Listen here. Weave point क्या है कि weaving velocity, the lower limit of the operating range occurs when the liquid leakage through the column holes become excessive. लिक्विड फ्लूइड की जो मिनिमम वैल्यू होगी वो तब होगी जब लिक्विड होल के थ्रू बहुत तेजी से निकलने लगे, एंड दिस इज नोन एज वीप पॉइंट. द वेपर वेलोसिटी एट द वीप पॉइंट इज द मिनिमम वैल्यू फॉर द suitable operation. Means vapor and flooding, all the velocity we are only able to calculate on the behalf of vapor velocity. So it is a minimum velocity of vapor to avoid the weeping. Actually the whole area must be chosen so that, और वापस बताए वीपिंग जो वेलोसिटी होगा बच्चों डिपेंड करेगा होल एरिया पे. होल एरिया ज़्यादा होगा तो वेपर की वेलोसिटी कम होगी तो फिर वीपिंग होगा. कॉमन सेंस है. तो सो दैट द लोवेस्ट ऑपरेटिंग रेट द वेपर फ्लो वेलोसिटी इज स्टिल वेल अबव द वीप पॉइंट. तो हमें होल एरिया इस तरीके से चूज करना पड़ेगा ताकि अगर वेपर की वेलोसिटी कम भी है फिर भी वीपिंग ना हो. It means because the reason is that if the velocity of vapor is low, if it is going to pass through a small hole area, then obviously its velocity goes on increases. And even the lower velocity of vapor will be able to hold the liquid over the tray, and that's why the whole area will play a very important role to define or to decide the minimum velocity of vapor. Are you getting? So we should design the hole diameter such a way that even the lower velocity of vapor is enough, much more above the weep velocity. So several correlations are there to find out the vapor velocity at the weep point. कई सारे correlations available है, but the most important जो है that is given by the ADOZ, and here simplest to use and minimum design vapor velocity is given by this equation called as, here I am going to write here U H bar cap means minimum velocity vapor. It is a minimum velocity of vapor through the holes, and that is what K2 minus 0.90. ये याद करने की जरूरत नहीं है, बट आपको स्टेप में बता सकते हो कि हाँ there is a correlation is there on the behalf of that, minus DH upon rho V raised to power 1/2. Where UH cap is the minimum vapor velocity called as weep velocity, DH is called as hole diameter in mm, and K2 is the constant. That constant will depend upon the depth of clear liquid on the plate obtained. Obviously it will depend upon the hole diameter and depth of liquid. So K2 will depend upon, K2 को अगर निकालना, this is called as K2, and if you want to find the K2 then obviously we should know दिस ये कर्व आपको गिवन होगा, और यहाँ पे आपको पैरामीटर जो होगा बच्चे क्लियर लिक्विड की जो हाइट होगी HW प्लस HW. क्लियर लिक्विड की हाइट जो होगी वियर हाइट प्लस वियर क्रस्ट हाइट ओवर ट्रे. तो वट एवर हाइट इज देयर ऑन द बिहाफ ऑफ दैट वी कैन कैलकुलेट द वैल्यू ऑफ K2, एंड वंस वी विल कैलकुलेट द K2 then you can put here, and it is density vapor and hole diameter is already we have decided in the step number 3. Then we will calculate the minimum velocity of vapor, and then obviously we should check our operating velocity is much more than this velocity or weep velocity or not. If there is no such much difference, then obviously we should change the parameters. Okay, now then here weir dimension is very important topic. Weir dimension, at least we should have some information about dimension of the weir and weir crust. Now weir height first called as HW. The height of the weir determines the volume of the liquid on the plate. I have told you many times that how much volume or amount of the liquid will be on the plate, that will depend upon the height of the weir, and is an important factor in determining the plate efficiency. A high weir, because I told you it is very common sense. Suppose anyone asks you how the weir height will affect the efficiency of the plate, that is very simple, because if the depth of the liquid is high, then obviously the residence time, the time spent by the fluid element, vapor element, and the liquid will be large. But at the same time, the pressure drop will also be high. So although we are going to increase the efficiency of the plate by increasing the residence time, by increasing the wear height, but also drawback, although efficiency has been increased by increasing the wear height, because wear height increases, the volume of liquid hold up over the stage will increases, and that will increase the residence time for the vapor to pass through liquid. But at the same time, the pressure drop will also increases. Okay. But if anyone asks you how the wear height will increase the efficiency, then you can say if the wear height increases, then volume of liquid hold on the stage will increases, and that will obviously increase the residence time, and that's why the efficiency will be good. Okay. Now, so a high wear will increase the plate efficiency. As I told you, a high wear height will increase the efficiency, but at the expense of higher pressure drop. As I told you earlier, everything is very simple. For columns operating above atmospheric pressure, अगर कोई column atmospheric pressure से ऊपर work कर रहा है, the wear height will normally be between 40 mm to 90 mm. At least we should have some range, not exact value, but at least we should range that it should be in mm. And how much mm? 40 to 90 mm. Means wear height should be normally between 40 mm to 90 mm. It is very important. 40 mm to 90 mm. Wear height is recommendable. Now, but 40 to 50 is more common. 40 to 90, but जो mostly use करते हैं, that is 40 to 50 is more common. For vacuum operation में the lower wear height is used to reduce the pressure drop. वैक्यूम ऑपरेशन में जो होगा वेयर की हाइट हम लो रखते हैं, वाइल एटमॉस्फेरिक और प्रेशर एटमॉस्फेयर से ज़्यादा है तो हम वेयर की हाइट थोड़ा सा ज़्यादा रखते हैं. अब रीजन अब इसे क्या सोच सकते हो, फॉर वैक्यूम ऑपरेशन लोअर वेयर हाइट्स आर यूज्ड टू रिड्यूस द प्रेशर ड्रॉप. पहली बात तो वैक्यूम कॉलम में if we are going to operate our column at the low pressure, then density of vapor will be low, and if the density of vapor will be low, then obviously for the same area velocity of vapor will be high. Then the pressure drop will be more, because pressure drop is proportional to velocity and also the liquid head over the tray. That's why since velocity is high and if the head will also be high of the liquid, then pressure drop will be more across the stage. So that to reduce the pressure drop in the vacuum column, we should reduce the height of the weir. Okay? Because in the low pressure column the velocity is enough, and if the velocity is enough, then turbulency will be sufficient so that the efficiency will be high. Then no need to go for the high liquid head. High liquid head is only high liquid head, it means wear height is required for the column which is going to operate more than atmosphere. Reason is that as the pressure is high, in this condition the velocity of vapor will be low, and since the velocity of vapor is low, then this vapor will not able to break into the larger smaller bubbles. It is only going to break, the vapor will be break in the small diameter, small size bubbles only when the velocity of vapor is large, and it is large only in the vacuum column. But as far as when we are going to operate a column at the very high pressure, more than atmospheric pressure, in that condition the velocity of vapor is not too high, and so that in order to increase the resistance time or plate efficiency, we should increase the wear height. So that is the reason you can give. For vacuum operation, lower wear heights are used to reduce the pressure drop. Already I told you. And 6 to 12 mm, very important thing. This point we should note it. And the reason also I told you, in vacuum operation the wear height is low, and while in the atmospheric, any column which is going to operate at that pressure more than atmosphere, we should use the high value of wear height, called as 40 to 90 mm, and it is only 6 to 12 mm. This the point we should note it. Now next is called inlet wears. Inlet wears are recessed pans are sometimes used to improve the distribution of the liquid across the plate, but it is very seldom used. कभी कभी use करते हैं. Inlet wears are not very important, only the wear height here. Now the wear length. The two things is there, wear height and wear length. Actually it is very easy to understand. Let's say it is a pit here and this is your down comma area, and that is your wear, and this is the liquid which is going to hold up. So that is called as wear length. LW is called as wear length, and it is called as vertical height and horizontal height. Horizontal height is called as wear length, and vertical height is called as wear height. SW, is it right? Now, wear length is the with the segmental downcomers, and the length of the wear fixes the area of downcomer. Actually, if you want to find the area of downcomer, the length of the wear will fix the area. कितना length होगा? According to this, we can calculate the area of downcomer. The chord length will normally be between 0.6 to 0.85 of the column diameter. जो chord length होगा, ये जो chord length है, यहाँ से अगर लेते हो chord length, this will be nearly, this is able to this called theta, and this is your chord length. This chord length will be what? 0.6 to 0.85 of the column diameter. A good initial value is 0.77, equivalent to the downcomer area of 12%. Means that 12% downcomer area is good of the total column area. Downcomer area should be 12% of the total column area. And the relationship between the wear length, called as LW, and downcomer area is given in the figure. Downcomer area में wear length में क्या relationship है, that is given here in the figure. You can go for this. This one is here. So that is not the important, but we should know कि how we should choose here. Or for if designing, tough क्या है? Tough is only in the sense of iteration. Otherwise, we should have everything on the behalf of that. We should go for that. Now, next is called a hole size. A hole size used vary from 2.5 to 12 mm, and 5 mm is most preferred size. जो range होगा hole size का, that is 2.5 mm to 12 mm. But 5 mm is most frequently used hole size. Larger hole are occasionally used for fouling system. अगर fouling system fouling ज़्यादा होगा, fouling fluid ले रहे हैं, then we should go for only larger, otherwise not. Hole or drilled or punched, hole को हम drill करते हैं, punch करते हैं. Punching is cheaper as compared to the drilling, but the minimum size of the hole that can be punched will be depend upon the plate thickness. और thickness भी depend करेगा, वही punching ये part है mechanical engineering का. We should not be bothered for that. Now, तो मेन थिंग इज होल साइज जो है वो, इसमें से होल साइज क्योंकि हम तो प्लेट की लेआउटिंग करेंगे तो हम प्लेट की होल साइज क्या लेंगे, तो दैट विल डिपेंड अपॉन दिस, बट एटलीस्ट वी शुड गो फॉर 5 mm. रेंज हमें पता है, उस रेंज में से कोई भी वैल्यू हम चूज कर सकते हैं. और उस कोई वैल्यू चूज करने का मतलब क्या है कि बिकॉज इट इज अ ट्रायल एंड एरर मेथड, हम जो भी चूज करेंगे ऑन द बिहाफ ऑफ दैट वी शुड कैलकुलेट द फाइनल रिजल्ट. इफ फाइनल रिजल्ट इज सैटिस्फैक्टरी देन गुड, अदरवाइज अगेन वी शुड चेंज द पैरामीटर्स लाइक दैट. तो एज आई टोल्ड यू दैट LW इज द वियर लेंथ. मैंने कहा था LW होगा जो वियर लेंथ होगा, एंड LH इज द दिस जो गैप है इज कॉल्ड LH, और D इज द डायमीटर ऑफ द होल. DS डायमीटर होल का डायमीटर है, सॉरी होल बोला हूँ, कॉलम का डायमीटर, सॉरी column diameter. तो DC actually column diameter, hole diameter, and wear length, and again the same here. तो on the behalf of that we should calculate the intersect angle. ये जो थीटा एंगल है वो कितना होगा, ये मैं अभी आगे बताऊंगा आपको डिटेल में. होल पिच जो होगा, इट इज अ होल एरिया टू द पिच एरिया. ये सारी चीज़ें इतना इंपॉर्टेंट नहीं है, बट हाँ ये देखो यहाँ से हम निकाल लेंगे होल एरिया, पिच एरिया, ये आगे सभी अभी आगे आएगा. अब हम बात करते हैं, यहाँ देखिए एक एग्जांपल देता हूँ, वहां से सारी चीजें क्लियर होंगी आपको. ये प्रॉब्लम जो मैंने लिया है, दैट प्रॉब्लम आई हैव टेकन फ्रॉम द वन लेक्चर ऑफ द एनपीटीएल। एक एग्जांपल आपके पास आरसी वालों में भी है, प्रॉब्लम कोई भी होगा, मैथडोलॉजी सेम है। देखो, फ्रॉम दिस प्रॉब्लम यू आर एबल टू नो व्हाट स्टेप वी शुड फॉलो ड्यूरिंग डिजाइनिंग, बिकॉज प्रॉब्लम विल मेक अ फ्रेम। अगर प्रॉब्लम सॉल्व करोगे तो वहाँ से एक आइडिया दिमाग में आएगा कि हम क्या क्या स्टेप को फॉलो करेंगे, क्या क्या हमने किए थे डिजाइनिंग करते समय। तो जो प्रॉब्लम क्या डिजाइन का, डिजाइन कंटिन्यूअस डिस्टिलेशन कॉलम, आपको एक डिजाइनिंग करनी है किसी कॉलम की, टू रिकवर द एसीटोन फ्रॉम 50 मोल% ऑफ एसीटोन वाटर मिक्सचर। तो आई हैव एसीटोन वाटर मिक्सचर ऑफ इक्विमोलर अमाउंट and it is available at 30 degrees Celsius. The feed stream flow rate is, it is a feed temperature. Flow rate of the stream is 25,000 kg per hour. The top product should contain at least, जो मेरा ऑब्जेक्टिव है कि at least 95% of the more volatile component should be in the overhead product. Means HG should be 0.95 and the bottom product should be contain less than 1% of acetone. It means HW should be less than 0.01, means very negligible. Consider revolver as equivalent to one stage. आपको revolver को as a stage की तरह treat करना है. This column is operated at atmospheric pressure, means top tray पे, जो top tray पे pressure जो है वो atmospheric pressure पे है. And bottom पे कैसे निकालोगे, pressure drop निकाल करके एक stage पे जितने stage होंगे multiply करके उसको add कर दोगे, क्या जाएगा bottom पे pressure. कॉलम एफिशिएंसी को हम एज्यूम कर रहे हैं 60% है एंड द प्रेशर ड्रॉप पर प्लेट इज 1.25 किलो पास्कल मे बी एज्यूम्ड। हियर इट इज गिवन दैट प्रेशर ड्रॉप पर प्लेट इज 1.25 किलो पास्कल, इट इज आल्सो गिवन टू यू। यू कैन टेक द मिनिमम लिक्विड फ्लो रेट एज 70% ऑफ मैक्सिमम रेट। जो मिनिमम लिक्विड फ्लो रेट होगा, मिनिमम लिक्विड फ्लो रेट एज 70% ऑफ मैक्सिमम रेट बोथ अबव एंड बिलो द फीड पॉइंट। मीन्स जो ऑपरेटिंग वेलोसिटी होगी वेपर की, मिनिमम लिक्विड एंड लिक्विड फ्लो रेट इज 70% मैक्सिमम रेट बोथ अबव एंड बिलो द फीड पॉइंट। आई विल डिस्कस लेटर ऑन व्हाट इज मीनिंग ऑफ दैट। द वेपर लिक्विड इक्विलिब्रियम डेटा इज गिवन हियर। ये वेपर लिक्विड, ये y है, ये x है, ये आपका TXY डायग्राम दिया हुआ एक्चुअली इस तरीके से आपको एसिटोन वाटर के लिए इस तरीके से ट्राइलाइन मिल जाएंगे। ट्राइलाइन से हम इक्विलिब्रियम कर्व को ड्रा कर लेंगे y और x पे। ये हमने ऑलरेडी बता चुका हूँ क्लासरूम में भी, सॉरी डायगोनल लाइन पे इस तरीके से मिल जाएगा कर्व। क्लियर है वाई एक्स डायग्राम। तो पहली बात तो, और डेटा जो क्या गिवन है कि लेटेंट हीट ऑफ वाटर इज गिवन, लेटेंट हीट ऑफ एसीटोन इज गिवन, स्पेसिफिक हीट ऑफ वाटर इज आल्सो गिवन एंड स्पेसिफिक हीट ऑफ एसीटोन इज आल्सो गिवन टू यू। नाउ फर्स्ट ऑफ ऑल व्हाट द स्टेप शुड बी, वी शुड कैलकुलेट द नंबर ऑफ स्टेजेस। A mass balance will also require F equal to L plus V, we know very well, L plus D, sorry D plus W. Then F into ZF, D into HD, W into HW. F feed flow rate is given 2500 kg per hour. We should change in the molar flow rate because equimolar mixture is there. That's why this ZF is 0.5 on the behalf of molar mole fraction, not mass fraction. And F is given 25,000 on the behalf of mass flow rate. So we should change the molar flow rate. For this we should know the average molecular weight, that I will discuss. So first of all that is a part of, here it is given the feed composition is 0.5, ZF 0.5, XD is 0.95 and obviously here water जो होगा 0.05 होगा और bottom में क्या होगा, it is maximum जो होगा 1% होगा, then जो water होगा वो 99% होगा। Now bubble point of the feed जो होगा that is given from data, because bubble point मैंने कहा था, मान लो ये आपके पास ये feed है, feed bubble point temperature means ये y और ये x किलो में होंगे, ये हो गया bubble point temperature। तो bubble point temperature since feed ZF is given in the very first lecture of the distillation I discussed, it is 0.5 and on the behalf of 0.5 it is your 59.95 degrees Celsius. So it is your bubble point temperature is the 59.95 of liquid mixture. Clear है? So here it is given the latent heat of the feed it means latent heat of the feed in sense means what? because the feed consists of 50% water and 50% acetone, then correspondingly latent heat of acetone and latent heat of water we have used here to find out the latent heat of the feed, because feed is not pure, feed is a mixture. That's why we should use this concept here. And then also we can calculate the specific heat of the mixture in the same way. Specific heat of the water and acetone is given correspondingly, and 0.5 correspondingly we have multiplied by the mole fraction. We have calculated the molar specific heat of the mixture. Okay, now and as far as Q is concerned, because ultimately the first step to design the column is to find the liquid and vapor flow rates. And to find the liquid and vapor flow rate is very important to have the value of R, reference ratio, and the Q. Then how we find the Q? Q is defined as, I told you, latent heat of the feed to convert the saturated liquid into vapor, and in the numerator it is the heat required to produce 1 mole of given feed. Means feed को vapor बनाने के लिए कौन सा vapor? Saturated vapor बनाने के लिए how much energy should supply, that is here. And how much heat is required? Heat required to produce 1 mole of the feed is what? Heat required to produce 1 mole of the feed. Now my dear student, as we know that the feed, listen here, it is a column is there. I told you column. Feed is temperature is 30 degrees Celsius in the problem they have given. I have discussed when I was dictating the question. 30. But the bubble point temperature is what? It is a 59 point something, 95. So first of all we have to increase the temperature from the feed temperature to bubble point temperature. It requires the sensible heat, and then it requires the latent heat to make it saturated vapor at this temperature. The same thing here. The first is sensible heat, mCp dt, and since it is for 1 mole, then 1 into, and it is your temperature difference from the bubble point to the feed temperature into Cp of the mixture. I have already calculated, plus latent heat is for the evaporation is given here, because I have already calculated the latent heat of evaporation of the mixture. So latent heat and plus sensible heat both is required to convert the at a given temperature to in vapor phase. And the latent heat of feed is obviously given here. Latent heat of the feed means just like here, it is 34885. And then since feed is subcooled liquid, because temperature is below bubble point, then Q will be more than 1. It is very obvious. Q will be more than 1 because feed is subcooled liquid. Because bubble point, when temperature of the liquid is below the bubble point temperature, feed temperature below the bubble point temperature, then obviously it is subcooled liquid. So it is subcooled liquid. Q is found to be 1.01, and from this we can calculate the slope Q line, Q upon Q minus 1. It is your slope, and top operating line just touches the.
सर कुछ स्टूडेंट्स को प्रॉब्लम हो रही है, कुछ के पास में वीडियो पहुंच रही है, तो बोल दीजिए कि आज हम यहीं तक करते हैं, फिर नेक्स्ट क्लास में प्रोसीड।
पहुंचने रही वीडियो,
कुछ को पहुंच रही है, कुछ को नहीं पहुंच रही। जैसे कि मैंने अपने मोबाइल पे चेक किया तो चल रहा है, सर के मोबाइल पे नहीं चल रहा। तो ऐसे कुछ स्टूडेंट के साथ भी यही प्रॉब्लम हो रही है, तो हो सकता है सर्वर एंड से कुछ प्रॉब्लम चल रही है। तो एक बार आप बोल दीजिए, कल क्लास में नोटिफिकेशन।
तो अभी बंद कर दें?
हाँ, एक बार उनसे बोल के।
Okay, now hope there is a problem in from server end that कुछ बच्चों के पास वीडियो पहुंच रही है, कुछ बच्चों का वीडियो नहीं पहुंच रही है शायद, and that's why I will continue this lecture by tomorrow, because it is a part of design and it is very important topic. That's why I am not able to continue it, क्योंकि हमें दोबारा करना पड़ेगा, and इसलिए please cooperate with us. और ये हम आपके लिए कर रहे हैं, इसमें मेरा कोई फ़ायदा नहीं है, हम आपके लिए कर रहे हैं। आप बैठे हो, आपको कुछ नॉलेज मिल जाए, तो इसलिए प्लीज़ कोऑपरेट विद अस, एंड जिससे कि सारे बच्चों के पास वीडियो पहुँचे। तो इसके लिए हम थोड़ा सा सर्वर एंड से हम दोबारा कुछ चेक करते हैं। सॉरी फॉर इंटरप्शन, वट एवर आई हैव डिस्कस जस्ट ट्राई टू रिकॉल, ट्राई टू रिवाइज। बंद कर दिया।